ride a river over you.
Good morning, everyone, and welcome to this Sunday emission, special morning Sunday edition, or Sunday morning edition, excuse me. How are you doing? I hope you're doing fine and well. Today, I have two articles and one curious note or article or news about Europe that you're gonna find very strange and maybe a little bit dark too. So let's start with that indeed. No time to waste. Let's go. Europe is set to welcome Dracula Land, a massive Dracula-themed resort near Bucharest, Romania. Of course, in Romania. What else? Announced in December 2025 as part of a €1 billion euros project, it will feature 6 themed lands and over 40 attractions, including Gothic castles, dark rides, and roller coasters inspired by Transylvania legends and Bram Stoker's novel. Well, that is a new one. The multi-day resort will also offer 1,200 themed hotel rooms, an aquapark, spa, 22,000 feet entertainment arena, shopping district, and more, aiming to open by 2027. Haha! Yeah, you should go with your family there. Maybe be careful with the disappearance. Okay, that was just fun news I found. I wanted to share with you. Maybe not a lot of you saw it. I hope not. So there it is. Okay, let's go to our main subject here. Is neuroscience, psychology, the brain. You know, that's my area of articles I wanna read with you to you. So let's start with this one. How the brain, from Quantum Magazine by, where's the author? Jasmine Saplagoglu. What? Saplagoglu. Here it is. From October 17th, 2025. This is a staff writer from Quantum Magazine. Jasmine. Let's start. How the brain moves from waking life to sleep and back again. Neuroscientists probing the boundary between sleep and awareness are finding many types of liminal states, which help explain the sleep disorders that can result when sleep transitions go wrong. Very interesting. Let's see what we have here. The pillow is cold against your cheek. Let me zoom in a little bit. Okay, so you can read it too. The pillow is cold against your cheek. Your upstairs neighbor creaks across the ceiling. You close your eyes. Shadows and light dance across your vision. A cat sniffs at a piece of cheese. Dots fall into a lake. All this feels very normal and fine, even though you don't own a cat and you're nowhere near a lake. Oh, so the very same dreams awakes you. You start your journey into sleep, the cryptic state that you and most other animals need in some form to survive. Indeed, you can let a cat sleep and wake it up before he dreams, and after a week, it's gonna be dead, sorry. Sleep refreshes the brain and body in ways we don't fully understand, repairing tissues, clearing our toxins, and solidifying memories, and also predicting programming too, for sure. You know, analysis from what can happen in the future. But as anyone who has experienced insomnia can attest, entering that state isn't psychologically or psychologically simple. What? Strange. Let's continue. The fall asleep, everything has to change, said Adam Horowitz. To fall asleep, everything has to change, said Adam Horowitz, a research affiliate in sleep science at the Massachusetts Institute of Technology. Okay, I'm awful today. I can't read. I have to find my flow. I think it's the music. It's not the appropriate one. I'm gonna change music. Sorry. Plantasia. Okay, let's go with our classic lounge music. I think this is more appropriate. Appropriated? Okay, don't worry. The flow of blood to the brain slows down, and the circulation of cerebrospinal fluid speeds up. Neurons release neurotransmitters that shift the brain's chemistry, and they start to behave differently, firing more in sync with one another. Mental images float in and out. Thoughts begin to warp. Our brains can really rapidly transform us from being aware of our environments to being unconscious, or even experiencing things that aren't there, said Laura Lewis, a sleep researcher at MIT. This raises deeply fascinating questions about our human experience. It's still largely mysterious how the brain managed to move between these states safely and efficiently. But studies targeting transitions both into and out of sleep are starting to unravel the neurobiological underpinnings of these in-between states, yielding an understanding that could explain how sleep disorders such as insomnia or sleep paralysis can result when things go awry. Sleep has been traditionally thought of as an all-or-nothing phenomenon, Lewis said. You're either awake or asleep. But the new findings are showing that it's much more of a spectrum than it is a category. Riding the brainwave. That sounds cool. In the 1930s, the millionaire Wall Street tycoon, lawyer, and amateur scientist Alfred Lee Loomis liked to scan the brains of his guests as they napped on his upstate New York mansion. Okay, extravagance. He was pioneering the use of a machine known as an electroencephalograph to study sleep. Okay. It was like a toy for him, no? A new toy. Technological toy. Every napper wore a cap with electrodes, which could non-invasively measure the brain activity. The machine would use a pen to physically scribble waves with peaks and thoughts onto paper, scrolling at a rate of 1 centimeter per second to create an electroencephalogram. EEG, the wave of sleep. Brainwaves recorded by electroencephalograph represent the activity of neurons. Sleep scientists use these waves to sort sleep into stages. Okay? This is how it looks when we are awake. This is when we are dreaming. The rapid eye movement is because we are creating images in our brain. So this movement of the eyes, these rapid movements, are related to imagery. It's not sleep, it's a few seconds of our 8-hour sleeps. Okay, this is stage 1. Non-REM sleep. This is the non-REM or REM. They are very similar, the rapid eye, the REM and non-REM. No, non-REM is a slower frequency. I don't know. Stage 2, non-REM sleep. There are 2 non-REM. One faster than the other. 3 non-REM. Wow, 3 non-REM, a few seconds of REM. That's where we dream, I'm almost sure. And awake. You can see the differences. What is the most beautiful one? I think awake it looks more musical. I don't know. What do you think? Let's continue. The waves represented the gross activity of neurons as well as we fall asleep. As we fall asleep, neurons start to synchronize, which means they fire together and go silent together. No one knows exactly why this happens. As a person sleeps, this synchrony grows, producing brainwaves that are lower in frequency and higher in amplitude. Yeah, like this. The right part of your screen. Over the course of a night's sleep, the waves will speed up and slow down in a cyclical fashion, all night, every night. Loomis categorized the different types of brainwaves into what became known as sleep states and created a nomenclature to describe the phases of unconsciousness. Electroencephalography catalyzed sleep research. Electroencephalography catalyzed sleep research, measuring the waves recorded on an EEG, became a common way for neuroscientists to infer a person's brain or sleep state without invasive surgery. It became the go-to method for understanding both the activity of neurons as we sleep and the subjective experiences, such as dreams, that they create as we move through different forms of sleep consciousness. Sleep consciousness? In the early 1950s, the psychologist Nathaniel Kleitman at the University of Chicago and his student Eugene Aserinsky first described the sleep stage categorized by rapid eye movement or REM sleep, a cycle the brain repeats multiple times throughout the night and during, every 90 minutes or something like that, more or less, of course, and during which we tend to dream. In REM sleep, brainwaves are faster than in non-REM sleep and look more like those produced when we are awake. Yes! Because we are experiencing and viewing things and listening to things like we would be awake. A few years later, Kleitman and the sleep researcher William Dement also at the University of Chicago, put together an improved sleep stage schema. 4 non-REM sleep stages based on Lumi's original work and 1 REM stage, a modified version with the last 2 non-REM stages combined into a single stage, is still in use today. So instead of 1, 2, 3, 4, I didn't understand if the new one has 4 or the new one has 3. But doesn't matter. Let's continue. However, by creating sharp boundaries, the schema obscured the subtleties of what happened between them. It became a norm in the field that you have 3 options. Okay. You are either awake, in non-REM sleep, or in REM sleep, said Thomas Andrillo, a cognitive neuroscientist at the Paris Brain Institute. Whoa, Paris Brain Institute. Thought there was some evidence that the brain could exist in a state that mixed sleep and wakefulness. It was largely ignored. It was considered too complicated and variable, counter the most researchers' tightly defined view of sleep. But little by little, a new wave of neuroscientists started questioning this status quo, Andrillo said, and they realized, well, maybe that's where things are interesting actually. Drifting off. Oh, Salvador Dali. The other articles is about Salvador Dali. I'm almost sure, or not? No, but I have another article about Dali, and it's here if I'm not mistaken. I had an article about... here it is. Yeah, it's the same article or not? Let me check this. My brain is falling asleep. How the brain moves from... Yeah, we are in this. I thought it was a coincidence. Sorry. Salvador Dali might agree. You should read his autobiography, A Diary of a Genius, or something like that. It's very crazy. Salvador Dali might agree. Around the time that Loomis was conducting EEG experiments in his mansion, the surrealist artist was experimenting with his own transitions into sleep, as he described it in his 1948 book, 50 Secrets of Magic Craftsmanship. Oh, I have to read that one. He would sit in a bony armchair, preferably of Spanish style, while loosely holding a heavy key in one palm above an upside-down plate on the floor. What? A bony armchair, preferably of Spanish style, while loosely holding a heavy key in one palm above an upside-down plate on the floor. Okay. As he drifted off, his hands would slacken, and eventually the key would fall through his fingers. The sudden clack of the key hitting the plate would wake him. What is this, a torture? Convinced that being aroused during this period revived his psychic being and boosted creativity, Dali would then sit down and start painting. Wow, I didn't know that. Other great minds, including Thomas Edison and Edgar Allan Poe, shared his interest in an experimentation with what is known as the hypnagogic state. Oh, that's the hypnagogic state. The early window of sleep when we start to experience mental imagery while we're still awake. The in-between. In 2021, A group of researchers at the Paris Brain Institute, including Andrew Long, discovered that these self-experimenters had gotten it right. Waking up from this earliest sleep stage, known as N1, seemed to put a people in a creative sweet spot. People who woke up after spending around 15 seconds in the hypnagogic state were nearly 3 times more likely to discover a hidden rule in a mathematical problem. A couple years later, another study led by Horowitz at MIT found that it's possible to further boost creativity in people emerging from this state by guiding what they dream about. Exactly what I do in my work. Teaching self-hypnosis so you can guide yourself through a kind of dreaming state, but without losing consciousness. And when you come out from this state, your pain is gonna be less or gone. Physical pain can disappear in these periods of hypnagogic state. That's a fact. It's not exactly clear why hypnagogia appears to boost creativity. One possibility is that the process of falling asleep requires us to release control over our thoughts, said Karen Konkoly. That sounds great. Who studied lucid dreaming as a postdoctoral fellow at Northwestern University and now consults for the sleep startup Dust Systems, co-founded by Horowitz. As our executive control over our mind relaxes, we can perhaps access a broader semantic network of information, which could help creativity. Andrew Long agrees that the sleep transition produces a state of freewheeling consciousness that unshackles the brain from its regular ways of thinking. You go out of the box. Like houses slowly shutting off their lights as a town falls into slumber, the brain gradually turns to night mode. Sleep starts at the center of town. Neurons deep in the brain, such as those in the ancient control center known as the hypothalamus, fire signals to suppress arousal circuits. Nearby brain regions, such as the thalamus, which relays information from your senses to the rest of your brain, shut off first. Minutes later, the cortex, which is involved in more conscious, high-order thinking, follows suit. It shuts down from the front of the brain, where planning and decision-making occurs, to the back, where the senses such as vision are analyzed. What a beautiful image to see. We should have an animation or MRI or something, right? During this transition, as some parts of the brain shut down while other parts remain awake, we can sometimes experience dream-like thoughts. In this hypnagogic state, many people are 1 foot in dreams and 1 foot in the world, Horowitz said. Some people hear things, others have visions. These are like dreams but lighter, projections against the scaffold of the real world, which is still in our grasp. We could think that there's a function to these mental experiences, said Siddhartha Ribeiro, a neuroscientist at the Federal University of Rio Grande do Norte in Brazil. But maybe there isn't. Maybe it's a byproduct of what's going on in the brain. I don't think so. But who knows, right? With your eyes shut and your senses powering down, you're no longer getting much input from the outside world, but you're still getting signals from inside the brain, maybe remnants of the day's experiences. Ribeiro and his team recently reported that a person's daytime experience can show up in hypnagogic imagery early in the process of drifting to sleep, adding to the other studies that made similar findings. Some researchers are using this state between sleep and wakefulness to study the nature of consciousness itself. If you can track what's going on in the brain when you go from those two opposite worlds, that would give you a lot of insights as to how consciousness fluctuates, said Nicolas Decat, a graduate student studying sleep and consciousness at the Paris Brain Institute. In preliminary research that's not yet peer-reviewed, Decat used an EEG to record the brainwaves of more than 100 people as they were falling asleep. Following the techniques of Dali and Edison, he had participants hold bottles so that as they drift off, the bottles would fall and make a sound to wake them up. Oh, let's make a little experiment with your dreams. By comparing the participants' brainwave with their self-reports about what crossed their minds, Decat realized that some dreamlike imagery had occurred while they were technically awake, and some voluntary thinking had occurred while they were technically sleeping. Cool. Like lucid dreams, right? For example, one participant reported ants crawling on her back, even as the EEG documented the fast and frequent brainwaves of wakefulness. Cool. Another reported having conscious thoughts about how they were falling asleep while they were technically asleep, based on a slow and infrequent brainwaves. The unpublished data suggests that sleep state may not be the best way to categorize sleep consciousness. Being awake or asleep does not fully determine what crosses your mind, Decat said. Exactly. In psychotherapy or hypnotherapy, you can have a very deep transhypnotic state, and even though not achieving some meaningful change in your life, or you can have a very light, shallow, hypnotic trance state and achieve a lot of change, stop smoking, relieving pain, as I said before. So that makes sense. Decat said the data challenged the popular view that when you're awake, you have certain thoughts. When you're asleep, you have dreamlike imagery. It's not necessarily like that. The transition to sleep can last for tens of minutes. Wow! That means it's fairly easy for researchers to study, far easier than the process of waking up. Oh! Which happens much more quickly. And sometimes, not Sundays. And in a less controlled way, it's much harder to predict when someone's going to wake up. Wow! Good morning, sunshine. Aurélie Stéphane, a postdoctoral researcher at the University of Lausanne in Switzerland. Okay, Lausanne is very famous for digitizing the brain. A very important project, digitizing the whole brain. They're starting with 1 cubic centimeter of a mouse brain, they say. But it's a very deep project. Okay, these dudes at this university grew interested in the wake-up process when she was studying a phenomenon known as paradoxical insomnia. Ooh. Unlike people with insomnia who are up all night without sleeping, people with paradoxical insomnia believe that they are up all night even though their brainwaves show that they are asleep. What? I didn't know that exists. This is amazing. Oh, the brain. The brain is the most complex thing in the universe, according to the brain. That's a good joke. They sleep as much as good sleepers, so it's a mystery, Stefan said. What? Paradoxical insomnia. What a beautiful, well, not beautiful thing, but very interesting thing. Like biological anomalies that are very interesting for biologists, but doctors or medical doctors see these anomalies as such, you know, you have to cut it, change it. So, to explain my admiration for this phenomena, to understand this problem, she needs to first study a more typical wake-up process. When a good sleeper wakes up, what is their brain doing? In a recent study, she examined more than 1,000 different awakenings or arousals, transitions from being asleep to being awake, on a time scale of seconds. She observed a curious slow brainwave in the data from good sleepers as they woke from non-REM sleep. Based on past animal studies, Stefan and her team hypothesized that this slow wave emanated from a spot deep in the brain. After this signal, she saw the cortex wake up as brain waves grew faster from the front. Let me read this again, the part before and this one. Based on past animal studies, Stefan and her team hypothesized that this slow wave emanated from a spot deep in the brain. Okay, she saw the cortex wake up as brain waves grew faster from the front, which managed executive function, to the back, where vision and other senses are processed. Very detailed. I like it. When people woke from REM sleep, direct from dreaming, their cortex woke up in the same way, but without the preceding slow wave from deep inside the brain. What that could mean? Or what could that mean, The presence of this unique slow wave was correlated with how people felt when they awoke. Stefan found participants who showed the signal woke up less drowsy than those without it. What? Participants who showed the signal woke up less drowsy than those without it. What is drowsy? Sorry, my ignorance. Drowsy. Oh, what happened with my morning? I thought I was showing the image. I'm sorry. What a shame. I don't know what happened with my screen. Very strange. What? What happened? Sorry, I'm really sorry for this big problem. I just wanted to know what drowsy means. Drowsy definition, meaning drowsy half sleep, half asleep. Okay. Now what happened with my... here it is. Very strange things happening here in my computer. Sorry. This suggested, but didn't prove, that this might be an arousal signal that assists the wake-up process, Stefan said. They have done a very good job of finding this signature of the sleep-to-wake transitions, said Luis de Lecea, a molecular biologist who studies sleep transitions in animals at Stanford University and was not involved with the study. They created a detailed portrait, Lewis said, and showed why we don't always wake up the same way. Even when we think we are fully awake and wondering about the world, parts of our brain could be sleeping. Still, EEG recordings are coarse and can't prove the deep brain or provide great detail. However, previous studies that used fMRI and electrodes unearthed some of the deeper mechanisms from which such arousal signals might arise. They found that neural signals for waking begin in deep, inner regions of the brain, such as the hypothalamus and the brainstem. These areas wake up the thalamus, which projects the instructions to the cortex. When we are in REM state, right? Or in non-REM state, I think. Doesn't matter. Though typically faster than falling asleep, waking up can also take some time. Stefan's sleep signature took a few seconds to travel from the front of the cortex to the back. Few seconds? I really need to visualize this with an animation or something. But recovering consciousness and cognitive abilities and shedding all sleep inertia can take minutes to an hour, she said. This study and others also showed that slow waves usually associated with sleep can sometimes indicate arousal. Yes, very counterintuitive. The lines are blurry. To me, the most important signal of general health in a human is a good sleep. And appetite, of course, no? But sleep and appetite, to me, are the most important indicators of one person's well-being. Even when we think we are fully awake and wondering about the world, parts of our brain could be sleeping. This phenomenon, known as local sleep, is thought to occur so that overworked neurons in the brain can rest and be refreshed. It is not unlike how dolphins can sleep with only one brain hemisphere at the time. Oh, what? It is not unlike how dolphins can sleep with only one brain hemisphere at a time, or how some birds sleeps on the wing. The wing? That means while they are flying? Sometimes when we are really tired, some neurons need to refresh and recharge, even if we are still up and going about our day. These people are awake, they have their eyes open, they can be even doing things, Andrelon said, and yet parts of their brain are undergoing the classic slow waves of sleep, given that local sleep challenges what sleep actually is. Troubled transitions. As we wake up and fall asleep or even move between sleep states, different types of wave happen at the same time. It's like a mandala. As neurons synchronize and desynchronize in different regions in a cacophony of rhythms, this mosaic can lead to experiences such as hypnagogia, lucid dreaming, and sleep disorders. Oh wow. Sleep disorders are incredibly common, Lewis said. They really are often defined by problems with the state switching. Yeah, the more you wanna fall asleep, the harder it's gonna be. These disorders might manifest as insomnia, where people don't fall asleep properly, or as night terrors, sleep paralysis, or sleepwalking, where they don't awaken as expected. In many cases, parts of the brain are awake when they should be sleeping, or vice versa. Yeah, now I understand better the variety of sleep problems, understanding this wave theory, let's say. Insomnia is fundamentally a difficulty with initiating the transition into sleep or maintaining it. Yes, this is the most classical insomnia. In sleep paralysis, the cortex wakes up before deeper brain regions that control the body. Again, in sleep paralysis, the cortex wakes up. Yeah, you are conscious, but you can't move, right? The cortex wakes up before deeper brain regions that control the body, resulting in full consciousness without the ability to move. Wow! In paradoxical insomnia, the potential arousal signal Stefan observed in her new study is weak. So instead of waking them up completely, it makes them feel awake. Wow. She said, her team found the same signal in sleepwalkers, but in those cases it happened in an inappropriate time window during deep sleep, she said. They also found that the brain activity of sleepwalkers is similar to that seen during dreaming, suggesting that both states result from similar mechanisms of sleep consciousness. The cat is continuing to probe what that sleep consciousness look like. He is running a survey to learn more about the mental experiences people have while falling asleep. Those thoughts and mental images can be hard to remember because to do so, we have to wake up. I almost never remember a dream. I don't know why. Sometimes we wake up right as we are falling asleep or from the depths of our sleep cycle, times we are not really supposed to. Maybe it's a bedmate turning in their sleep that disturb us. Maybe it's the clink of keys on a hard floor. Maybe it's the brain itself miscalculating when it's supposed to arouse certain regions. Your sleep consciousness is disrupted. You pull back from the edge of sleep and your eyes blink open. Very interesting, very informative, very well. Very, very well. This is one of 2 articles for today, and this is the second one. Neuroscientists just opened our understanding of Pavlovian learning. Let's see. A recent study published in Nature Neuroscience suggests that the brain learns to associate a specific signal with a reward based on the amount of time that passes between rewards, rather than the sheer number of repetitions. How's the music doing? We have a couple of tracks left. 8 minutes of music, of this music. So more important is the timing than the number of repetitions. This challenges a century-old assumption about conditioning providing evidence that total learning over a given period depends entirely on timing. These findings could shift our understanding of both animal and human learning. Timing is everything. For over 100 years, scientists have generally accepted that associative learning operates through trial and error. Associative learning is the process by which a human or an animal learns to link a specific signal with a specific outcome, like a dog learning that a bell means dinner is ready. The prevailing thought has been that more practice leads to better learning. That might be true as well. Scientists previously developed a mathematical model suggesting that animals learn by looking backward in time to identify the causes of meaningful effects. In this framework, the brain does not try to predict the future effects of a cue, but rather works backward from a reward to figure out what predicted it. While testing this idea, scientists noticed that animals learned proportionally faster when the time between rewards was extended. Faster when extended? We had realized soon after publishing this paper that this model predicts that animals will learn cue-reward associations proportionally faster when the trials are spaced out, which should mean that over a fixed duration, total learning is independent of the number of experienced cue-reward pairings, said study author Vijay Mohan Ki Nambudiri, an associate professor at UC San Francisco. This observation prompted researchers to test whether a strict mathematical rule governs the rate of learning. They aim to determine if learning speeds up proportionally in relation to the time elapsed between cue and reward experiences. They designed a series of experiments to measure both physical behavior and brain chemistry in real time. Wow! We set out to test whether there's a rule governing learning rate control. We set out to test whether there is a rule governing learning rate control and whether learning rate scales proportionally with the time between cue-reward experiences. The researchers conducted their study using 101 adult male and female mice. They classically conditioned thirsty mice by playing a brief auditory tone followed by the delivery of sugar-sweetened water. The mice were physically held in a fixed position. Oh, poor mice. Ensuring the testing conditions were controlled and uniform across all subjects. As the mice learned the association, they would begin licking the water spout as soon as they heard the tone, anticipating the sugar water. To measure the underlying brain activity, the researchers used a technique called fiber photometry. They injected a special fluorescent sensor into the nucleus accumbens car. I don't know what that is. A brain region heavily involved in processing rewards. This sensor lit up when the brain released dopamine, a chemical messenger strongly linked to pleasure, motivation, and learning. Whoa, dopamine and learning. I didn't know that. Yeah, makes sense. One person can feel very cool, good when learn something new, right? This allowed the scientists to monitor exactly when the brain processed the tone and the reward. The researchers divided the mice into different groups based on how much time passed between the trials. Some mice experienced the tone and reward every 60 seconds, while others waited 600 seconds between pairings. The mice that waited 600 seconds learned the association in about 1/10 the number of tries compared to the mice on the 60-second schedule. How? Why? This indicates a proportional relationship where the rate of learning per trial increases as the time between rewards increases. I wanna understand this. As a result, both groups of mice learned the association in the exact same amount of total conditioning time, despite one group experiencing far fewer total tone and reward pairings. Yeah, the shorter one. The main finding of the study that learning rate, how much is learned from each experience, scales proportionally with the time between rewards, was very surprising. Yeah, it's like a positive procrastination, right? The more you are able to postpone your gratification, the stronger it's gonna be your I don't know, your capabilities, in some sense. Your motivation, maybe? I don't know. The main finding of the study that learning rate, how much is learned from each experience, scales proportionally with the time between rewards, it was very surprising, yes. Nambu did it all Saipos. While it was a prediction made by our retrospective learning model mentioned above, we expected our initial experiments to falsify that prediction and necessitate an update to the model. But no, the dopamine measures provide evidence matching the behavioral observations. In the mice with longer gaps between rewards, the brain required proportionally fewer experiences before it started releasing dopamine in response to the tone alone. The dopamine response actually emerged a few tries before the mice started physically licking the spout in anticipation. Trial by trial, we tracked how dopamine responses to cues evolved during learning under the same timing manipulations we used behaviorally. Nambudri said, "We found that dopamine signals follow the same learning rule. The rate and magnitude of changes in dopamine cue responses..." Sorry, the music is over. Let me change music. That was fast, 8 minutes. We found that dopamine signals followed the same learning rule. The rate and magnitude of changes in dopamine cue responses depended on the average time between rewards, not on the raw number of cue-reward pairings. This parallel between behavior and dopamine activity shows that the brain's reward system implements a time-based learning rule, revealing a simple biological underpinning for how animals learn from rewards. To ensure their results were not caused by other factors, the scientists ran several control experiments. They tested whether the mice simply learned faster because they received fewer rewards per day, which might make the sugar water seem more novel. The researchers also tested whether spending more time in the testing chamber without hearing tones played a role. Even when controlling for these variables, the proportional scaling rule remained consistent. The time between rewards consistently dictated the speed of learning per trial. The scientists then tested aversive learning by pairing a tone with a mild foot shock in freely moving mice. They observed the same proportional scaling rule in this scenario. Mice with longer times between shocks learned to freeze in response to the tone in proportionally fewer trials. In another variation, researchers tested partial reinforcement, they played the tone every 60 seconds, but only gave the sugar water 10% to 50% of the time. Because the actual rewards were spaced farther apart in time, the mice learned the underlying dopamine association in far fewer rewarded trials than mice receiving rewards every single time. Incredible. Traditional theories of learning assume the brain calculates a prediction error on a moment-by-moment basis. A prediction error is the difference between the reward an animal expects and the reward it actually receives. Again, a prediction error is the difference between the reward an animal expects and the reward it actually receives. The researchers compared these older models against their newer framework that calculates associations by looking backward in time only when a reward is received. When running computer simulations of these different theories, the traditional models failed to match the behavior of the mice. The traditional models could not explain why learning rates scaled proportionally with the time between rewards. The newer backward-looking model naturally predicted this exact proportional scaling, providing strong theoretical support for the experimental findings. A key takeaway from our study is that what really drives reward-based learning is how much time passes between rewards, not how many cue-reward pairings an animal experiences, Namburdi summarized. In simple terms, we found that when rewards are spaced farther apart in time, each individual reward leads to proportionally greater learning. Thus, if rewards occur 10 times farther apart, each reward leads to roughly 10 times more learning. This is amazing. As a result, when you look over a fixed amount of time, the total amount of learning ends up the same despite vastly different number of cue-reward experiences over a 20-fold range. This previously unknown learning rule suggests that the total number of experiences is not the key determinant of learning, which challenges some long-standing assumptions in neuroscience and reinforcement learning. Yes! The field had known that spreading pairings out in time speeds up learning per pairing, but it was still assumed that the final level of learning depends on the total number of pairings. Our experiments showed that instead, total learning is determined by time, not count. Readers might easily confuse these findings with the well-known spacing effect. The spacing effect is a broad educational concept suggesting that taking breaks between study sessions yields better learning than cramming. The new research points to something much more specific than a general benefit of taking breaks. We would like to highlight that our results are not simply a restatement of the spacing effect or its biological underpinnings, but instead that we have identified a previously unknown rule of learning. Mr. Nambudiri told SciPost. The spacing effect can be summarized in broad terms as spacing out experiences equal to better learning. Spacing out experiences equal to better learning. Nice. Which implies that when experiences are closer together in time, there are diminishing returns on their contribution to learning. Cool. We have to rearrange all the educational system. Great. However, our findings that learning rate scales proportionally with the time between rewards, specifically, require a fundamental shift from the above perspective because it necessitates, as we show, that over a fixed amount of time, number of cue reward experiences has no impact on overall learning. Good news for the students! One potential limitation is that the researchers tested this specific rule primarily in simple condition setups using mice. Yes, that's a good point. They also noted that the proportional scaling rule tends to break down at extreme intervals. Oh yeah, of course. Such as when mice waited an entire hour between rewards. Future research will explore where exactly in the brain this time duration is calculated. Yeah, good question. Scientists also plan to investigate whether this rule applies to drug rewards, which could offer insights into addiction and habit formation. Because nicotine patches deliver a constant stream of nicotine, for example, they might disrupt the brain's association between the act of smoking and the reward, blunting the urge to smoke. Applying these timing principles to artificial intelligence systems might also help machines learn much faster from fewer pieces of data. Current systems learn slowly because they make tiny refinements after billions of interactions. A model borrowing from these new biological findings could potentially accelerate artificial learning. The study duration between rewards controlled. The study duration between rewards controls the rate of behavioral and dopaminergic learning. Was authored by Dennis A. Burke, Annie Taylor, Hui-Jiong Gion, Xiu-La Li, Leo Sembik, Brenda Wu, Joseph R. Flodder, Gautam A. Naik, Richie Chen, and Vijay Mohan K. Nambudiri. So, that's all for today. I hope you enjoyed some parts. You can let me know. Oh, my battery is going out. Thank you very much, ladies and gentlemen. See you the next one. Goodbye.